Hi, welcome back everyone. This is our second video in the data link layer series in the topic error correction and detection. So, as let's first see what we talked last time. We saw the types of error: single bit error in which single bit got corrupted, burst error in which multiple bits got corrupted. And to detect and correct those, we applied error detection and correction methods, and we can check that we estimated that the probability of being a bit in the valid keywords. So retransmission, we can request the sender to send back the data again. So we started to talk about various coding techniques. That is, we were talking about block coding, in which we divided the data into k data words and add r redundant bits, and which became our n is equal to k plus r code word. So the last time, as this table we used, and we were able to detect whether the received data is one of those valid code words. So as we added one extra redundant bit in this, and the size of our code word became n equal to 3. So with n equal to 3, we were able to detect a single bit of error. And when we added 3 extra bits with n equal to 5, we were able to correct a single bit of error. So exactly, you will be thinking exactly how much bits we need to detect and correct. So what should be the size and how many redundant bits I should add so that I will be able to detect this many bits of error? Well, in general I can say the more the merrier, but well, there is a rule for that. And to know that, we have to get to know a term known as Hamming distance. So let's start with Hamming distance. What is Hamming distance? Hamming distance is the number of differences between two code words. Like, let's say 100100100. So these are our two given pair of code words, and the Hamming distance is, as this bit is same, this is different. So same, different, different. So the Hamming distance of this pair is 3. So Hamming distance is just the difference between given code words. And there is another method to do that if you're not going to count like this. It's a simple XOR operation. You may all be knowing what is XOR operation. That is 1 XOR of 0 gives 1, 0 XOR of 1 gives 1, 0 XOR 0 gives 0, 1 XOR 1 gives 0. So this is the XOR, I don't say table. So to directly find the Hamming distance, we can XOR the given two pairs. Let's say here 1 0 0 1 0 0 1 0 0 0. So by using this, the XOR of 1 0 is 1. So 1 0 is 1. This is 1 0 0 1 is 1. 1 0 is 1. So how many ones? 3. So we can say the Hamming distance is 3. Yeah, pretty easy. Now there is one more, I say, definition is minimum Hamming distance. This is just the same Hamming distance, but we are given many pairs like P1, P2, P3, P4, many pair of these code words. Minimum Hamming distance is, as you can guess, we will find the Hamming distance of every one of them, and the minimum among them will be known as minimum Hamming distance. So now to answer our question that how many bits I need to add to detect like one bit of error or something like that. So for that concept we used minimum Hamming distance. So like we want to find S errors, S bits of errors. So the table, the block code we designed for it should have D minimum, that is minimum Hamming distance equal to S plus 1. So let's see the Hamming distance between these two is 1, these two, and this 2 is 1 again, this 2 is also, this is 2. So the minimum was 1. So to detect S errors, as we detected how many? One error. So to detect S errors, so one error, the D minimum should be 2. The minimum should be 2. It was 1 in this, so we were able to detect single bit of error also. So if we want to detect, you can say 2 bits of error. So by using this formula, 2 plus 1 equal to D minimum. So the code word table we create, and by finding the minimum distance between each pair, after finding the minimum of those Hamming distances, it should be not greater than this 3 to detect, if you want to detect S, that is 2 in this case. So this is about detection. What about correction? We were able to correct 1 bit in this. Correction also use the concept of Hamming distance, in which to correct, let's say, T bit of errors. T bit of errors, the minimum Hamming distance should be D minimum 2T plus 1. That is the code word table we will have. The minimum Hamming distance should be this 2T plus 1. So what we got till now? To correct we need S plus 1 to correct S bits. S plus 1 is equal to minimum Hamming distance. And second, sorry, this was to detect, and to correct we need 2S plus 1 D min. So we need much more bits for correction than detection. So that's why the more data and implementation is more difficult in correction. Detection is easy. So the next thing we are going to talk about is the techniques used, that are linear block codes. Most of the block coding techniques, as we have discussed by using this table and all, use the linear block code, and as it is much more simpler and the implementation is simple than other coding techniques available. So linear block code. So the code words we used before are linear, belong to this subset or not of linear block codes. How do we know? Well, there is a simple thing we can do to check it. As in linear block code, the XOR of any two code words is another code word. Magical. So let's see. As our data was this 0 0 0 1 1 0 1 1, and our code was this 0 0. Let's create another 0 0 0 1 1 0 1 1 0 0 0 0 1 0 1 0 0 1 1 0. These are our data words and these are our code words. So whether this set of code words belong to linear block codes or not, so we can XOR any two code words and see if we can get enough. So if I XOR with 0, I will get the same, so there's no need to check with that. So let's say I XOR this and this, I will get 1 1 0, which is also part of this. And if I XOR this 1 0 0 1 1 0, then 0 1 0 0 1 0, which is also part of table. So the coding we used before also belongs to the linear block codes. This is how we check whether the given coding scheme belongs to the linear block codes or not. Well, the first one we are going to talk about is under this linear block codes is known as simple parity check. What is this? Well, simple parity check is an error detecting code. We won't be able to correct it, but we will surely detect it. So it is an error detecting code with n equal to k plus 1. That is, n is the, what is it, code word with k data words and one redundant bit we add. So how do we create this code? Okay, let's draw it. Let's say these are our 4 bits. Zero, 1, 2, 3. Okay, these are our 4 bits and they can be anything, 1 0 0 1, whatever. So these are our 4 bits and we will generate a one more bit to add to it, that is, as we saw, one bit, one redundant bit we are going to add. This will we can easily calculate this one bit with just by adding all of these. Like if these were 0 0 1, so it will be, if we add this all, addition 1 plus 1 is 0, then it's 0, so it will 0. And if it was this, like 1 plus 0 plus 1, then we will add as 1 plus 1 plus 1 is equal to 1. Simple addition of binary will be having 1. So after adding this parity bit, as we can see, 1 0 0 1 0, the number of ones in our code words become even, as in this 1 1 3 4, even again. So by adding this parity bit, the total code words, the number of ones become even. So we use this our This is the basic working. The bits goes there and there is a generator. It generate the parity bit. And adds it to this. So this is our final code word. And on the receiver side, this is received. It goes into a checker. It checks whether the sum of this is 0, as the ones were even. The sum of the whole things comes 0, and it will say that yeah, it is not corrupted. But if any of the bits changed, and so the sum will be changed and it will be 1, so we will be able to detect, yeah, some error occurred. Where occurred, we don't know. We are not correcting it. We are just detecting whether error occurred or not. So this is simple and a linear block code, simple parity check. Same thing, problem is that if 2 bits are changed and the sum becomes even, then again there will be a problem. We will not be able to detect. As we can only detect 1 bit error with simple parity check. As I said before, the more the merrier. So we can think of using a 2D table, like generating parity in 2D, 2-dimensional. That we can have a, let's say 1 1 0 0 1 1 1 1 0 1 1 1 0 1 0 1 1 1 0 0 1, or whatever. So like this, we are using 2-dimensional parity check. In this we make the ones even by generating parity 1 2 3 4 5. So one more, 1 2 3 4. Okay, so 1 1 1, so it's already even. 1 0 1 0 1 0 0 0 0 0, odd 1 odd 1. So this is much better approach as compared to simple parity check. As let's say if this is corrupted, this is changed to 1, then it will affect this as well as this. So it is much easy, much accurate in pointing out that the error has occurred. And what if the problem in previous one was as 2 bits were corrupted, we were unable to detect. So let's say 2 bits are corrupted. Let's say this also gets corrupted to 1. So of course the changes will be here, we won't be able to detect, but we will be here. So see, we can still detect if 2 errors are there. Let's say this also gets corrupted, so we will not be able to detect here, as this will cancel out each other, but we will detect here. So again we were able to detect, but yeah, the problem is here also. If we cancel in both dimensions, let's say this is also corrupted, So this one cancels this one row wise, so no detection here. This one cancels this one, no detection here. This one cancels this one, no detection. Okay. So wow, great, our data uncorrupted, but actually we were not able to detect in it. So this is two-dimensional approach, much better than the simple parity check in which this whole table is sent to the receiver. So in the next one we will be talking about Hamming codes technique. Hamming codes is also mostly like this parity check only, and about cyclic redundancy. Okay, see you next time.